Welcome to Chemical Process Safety. In this video, we'll start Chapter 6, which is all about fires and explosions. Now, I know that everybody probably knows what a fire is, but let's take a quick second to do a formal definition. A fire is the rapid exothermic oxidation of an ignited fuel. It's important to note here that the fuel may be solid, vapor, or liquid, any of the phases, but the combustion itself always occurs in the vapor phase. And that knowledge is important because studying how fires occur is one of the ways that we can work to prevent fires, which is one of the frequent hazards that occurs in a chemical plant. Up until now, we've had a couple of examples from the CSP videos and whatnot about chemical releases or dispersion models. But if you actually look on that website, a majority of the incidents have a fire involved that are on that website. So there's no shortage of case studies that we can look at with the fires and explosions module for this course. All right, let's talk about a little bit more detail. First thing we'll discuss is the fire triangle, which describes the three things that you need for a hazard. So you definitely need fuel, you need an oxidizer, and you need an ignition source. And that is because the combustion reaction is fuel plus oxygen goes to CO2 or NO2 or whatever plus water. Interestingly, if you can eliminate just one of the legs of this fire triangle, you have completely removed the hazard. So for example, if you remove the fuel, you have no hazard of a combustion going to occur. But this is much more difficult than it sounds. So what I just said, removing the fuel. Well, how are you going to remove a fuel from the chemical process, right? Maybe your chemical process is producing the fuel itself, and therefore removing the fuel totally removes the need for a process at all. Or the fuel may be an integral chemical to your process. So although that sounds appetizing, then you can never just remove the fuel from your process. Similarly, you might think removing the ignition source would be a good thing to do, and indeed that is a good thing to do as well. But there are so many ignition sources, and the minimum ignition energy for so many of these fuels is so low that you can never fully be sure that you do not have an ignition source. The static electricity could be something that could possibly ignite a fire. So even though you take care to have rules around the chemical plant, like no smoking, for example, would be one that nowadays is strictly enforced, you can never be totally sure that you do not have an ignition source. So because we've ruled out fuel and ignition from being possible, the last chance that we have to completely remove without a shadow of a doubt one of the legs from the fire triangle is removing the oxidizer. And that one does not seem very tractable at first, because in order to remove the oxidizer, you have to remove all the oxygen. And this is abundant in the atmosphere. And this itself is potentially dangerous because you can't just remove the oxygen from a room, for example. But you can remove oxygen from a closed storage tank. And actually, that's what we'll talk about in the next module that's going to be about inerting, is calculating how many cycles you would need to purge the oxygen out of a tank with nitrogen, for example. But anyway, just know that for now, that on the legs of the fire triangle, oxygen is the one that chemical safety process programs oftentimes try to eliminate. And that's not even to mention oxygen is only one of the possible oxidizers, right? We could still oxidize with chlorine, hydrogen peroxide, nitric acid, perchloric acid, etc. So just because you've removed the oxygen does not mean that you've removed the hazard. It also requires being aware of what the oxidizers are, and not storing oxidizers next to flammable materials, for example. Anyway, there's also something called the dust explosion pentagon, similar to the fire triangle, but dust can also explode. I'll have a CSP video that shows how that can occur. But in addition to fuel, ignition source, and oxidizer, for a dust to combust, we also need to add the legs of confinement and dispersion, and our fire triangle becomes a fire pentagon. So the video that I'll show you from the CSP is a sugar refinery where these 5 legs were all present, and it led to a fire and an explosion. So early on in chapter 6, there's a ton of definitions, and you may be tempted to skip those definitions, but I will encourage you not to do that. So a lot of the terms that are defined, like ignition, for example, you might think, well, oh, I know what ignition is, so I'm going to skip reading that. Don't do that because, again, a lot of these things are very specific to chemical process safety, and you might learn something that you didn't already know. So I don't plan to read these definitions to you, but I'll encourage you to read them. These are on page 221 and 222. For example, flashpoint would be a good one where I would imagine that many undergrads would say, oh, yeah, I know what the flashpoint temperature is, but if pressed, I don't think that you would be able to define it without learning about it. So please do have a look and read through all those definitions. Last thing I'll talk about in this short video, just getting us started, is this graph, which is figure 6-2 in the textbook. And this shows the relationships between various flammability parameters. So this is helpful for putting into context some of these terms like auto ignition temperature or flashpoint temperature. So let's talk more holistically about the plot first. So on the y-axis, we have the concentration of flammable vapor. This is all vapor phase, by the way. So as you move up the y-axis, you're getting more and more concentrated in your flammable thing. The x-axis is the temperature. So this region where it says miss is below the saturation temperature. So imagine here that this is cold but high concentration of flammable. Stuff is going to start to condense. And that's what it means by miss. So when I think of miss, I like to think about the gym that I go to has one of those steam rooms. And when you walk in, there's all this steam, which is actually condensed water because there's so much water vapor. There's more water vapor than the air can actually hold. So it starts to condense and floats in midair. So that's what this mist zone is. As you move higher and higher temperatures, then you bypass this curve, which is the saturation vapor pressure curve. Think back to Raoult's law from material energy balances. This is the same meaning for this saturation curve. So this is the completely vapor zone. This is the liquid zone. This is vapor-liquid equilibrium. Here we have the lower flammability limit, which we'll talk about in the next couple videos. But this is the minimum concentration that you would need to burn. So below the lower flammability limit, there is not enough fuel for combustion to occur. Right, so this is a safe part of this curve where we are not flammable. Conversely, this is kind of a weird one, but we also have an upper flammability limit. And above the upper flammability limit, we're also in a safe zone because there's not enough oxygen at this point. So a common question I like to ask and get you thinking is, if you had the choice to store a chemical either above the upper flammability limit or below the lower flammability limit, which one would you choose and why? So think about that one. Actually, I'll just give you a couple more seconds, maybe hopefully encourage you to pause the video, and then I'll tell you. I would prefer to have below the lower flammability limit because if you store something above the upper flammability limit, you can never guarantee that you are not going to disperse something. So if I were to lose containment of my gas that was at the upper flammability limit, it would start to diffuse and disperse, and then the concentration would drop. So I would go through the flammable zone. On the flip side, if I'm at the lower flammability limit or below already, I'm never going to spontaneously get more concentrated unless I add more gas. So for that reason, below the LFL is where we would prefer to be. In between the flammability limits, we are in the flammable zone, and this is what we want to avoid at all costs, because if we have a flammable mixture of fuel and oxygen, if we have an ignition source, we have the potential for a fire to start. Just looking back at some of the definitions that are important, the flashpoint temperature is listed here. This is the lowest temperature at which a fuel will give off enough vapor to form an ignitable mixture. So below this is where the LFL, by the way, meets the saturation curve. Below this temperature, I will never have a vapor that is above the LFL. You can prove that just by looking at this region of the plot. If here, obviously, I'm in the not flammable zone, but if I get more and more concentrated, well, now I start to condense and stuff is going into the liquid phase. Last thing I'll talk about on this plot is the autoignition region, which is particularly terrifying. Autoignition is what happens when combustion just happens by itself. And that is actually possible if the temperature is high enough and there's enough energy. So the lowest temperature at which autoignition could potentially occur is called the autoignition temperature. You might have seen this on safety data sheets or something like that. But definitely you want to make sure that you are operating your process below the autoignition temperature. And if possible, it would be good to operate below the flashpoint temperature, but that is oftentimes not possible at all. So if you have me for process design, for example, I always like to make you go back and look up the flammability diagrams and remember this and talk about what autoignition temperature and what flashpoint temperature mean, and whether or not in the process you design you have a potential for a hazardous fire. But anyway, I'll wrap this video up. Next couple videos, we'll talk about other types of flammability diagrams that we will use to solve problems.